Okay, so this mini lecture is going to look at another way that we can pictorially represent motion. We've talked about describing it and setting up an origin and a system and a world and a picture. We've talked about it in terms of motion diagrams and those strobe diagrams, the same word, same idea, two different descriptions, where we're showing dots and how it moves in the dark and where it is when the lights turn on. And this last way is going to pictorially represented is going to be in a graphical representation. So what does motion look like if I wanted to represent it graphically? And we're going to start with position. Position versus time graphs. So if I'm interested in the time of an object's motion, how is its position at every point in time from when I start carrying to when I stop carrying? What does that graph look like? So we use the Cartesian coordinate system to represent the graph. So that's that XY coordinate system. And because we're going to define the initial time as being time point 0, so when we start caring about the motion is when time equals 0. So there's not going to be, we're not going to define negative time before we start carrying. So don't have to worry about this half of the graph. On our graph, time will be on the x-axis. So time, and our unit, of course, is seconds. The y-axis is going to be position. Now, just like you learned how to graph when you first learned the Cartesian coordinate system, that cross point happens at 0, 0. So at 0, 0, this is where x equals 0. Anything, if we're, let's say, doing an example that's moving to the right or left, anything of the origin, this is our origin. Anything to the right is positive, and like the Cartesian system, anything above that 0 is positive. This is, in our case, for example, like to the right, east, north, so those conventions. And anything below the axis is negative. So if I wanted to represent an object's location at some point in time, let's say at the beginning of the motion, as being 3 meters right of the origin, then my object would be located, if these hash marks represented meters, in position, they would be located at that point, at the beginning of my motion. If my object was started at the origin when I started carrying, then it would be located at that point. If my object was 10 meters to the left of the origin, he'd be located somewhere down here. So if my object is ever to the right of the origin, they're above the axis. If they're to the left of the origin, they're below the axis. So that's our sort of first rule of thumb in a coordinate system where we're representing position versus time graphs. If it's above the axis, it's to the right of the origin. If it's physically located to the right of where we've defined the origin. If it's below the axis, it's to the left of the origin. Physically located at that point in time, left of the origin. So how do certain motions look? Physical motions, descriptions of motions, look on a graph. What if an object were standing still? Well, let's say an object is standing still at 3 meters. So our first scenario will be standing still. So if the object is standing still at 3 meters, when I start carrying, where is it located? At 3 meters. So here's time point 0. We'll put some times on our, we'll have each hash mark be 1 second. So 1 second, 2 seconds, 3 seconds. So at 1 second, if the object was still standing still after 1 second, he's still going to be at 3 meters. After 2 seconds, he's still going to be at 3 meters. This kind of looks like a strobe diagram. Well, what is he at a half a second? Well, if he's standing still, he's still at 3 meters. What about 1.5 seconds? Still at 3 meters. What about a quarter of a second? Still at 3 meters. We can see that if an object is standing still, his position is not changing as time goes on. It's staying the same value on my position time graph it's represented by a flat horizontal line standing still. The object is not changing location as time goes on. So it's at the same position represented on the y-axis as time goes on. Okay. Well, what about an object that is moving at a constant velocity? So we'll do that in pink. Now, how do we know where the object is starting? Well, we're still going to define where the object started when I started carrying time point 0. So let's say it started at the origin. So in this scenario, we'll use the origin as our initial position. Okay, here, let's just define this. Standing still at x equals to 3 meters. And we'll move at a constant velocity starting at x equals 0. Now, we know velocity has direction. So for this to define constant velocity, we need to know what direction it's heading. Let's say it's moving to the right for this example. Starting at constant velocity, starting at x equals 0, and moving to the right. All right. So a constant velocity tells us that for every point in time, we cover the same distance. So let's say we're going to cover 1 meter every second. So after 1 second, I've covered 1 meter. So my position is here. 1 meter to the right, because I'm moving to the right, in 1 second. So I ended up at the point 1 meter. In the next second, I keep moving to the right. I cover 1 meter in 1 second. So I end up here. In the third second, I keep moving to the right. So I end up with 1 meter more. So now I've moved to 3 meters after that third second. Now what about a half a second? If I'm moving at a constant rate, then if I'm moving 1 meter in 1 second, I'm moving a half a meter in a half a second. And after this half a second, I've moved another half a meter. And after this half a second, I've moved another half a meter. And we can see that a constant velocity, I'm not very good at my graphs today, a constant velocity is moving at a constant rate, that's what it means, the same positional change for every change in time. And this sounds very similar to when we learned about graphing, whenever you learned about graphing in terms of a slope. How does the y-axis change in terms of the x-axis? If it changes the same amount in the same amount of time, we have a constant slope. So a constant slope, or a straight line that is not horizontal, this represents constant velocity. Now, we mentioned that direction was important. What if I changed this scenario and said instead of moving to the right, starting at 0, we had the object moving left? Starting at 0. Well, in that case, we'll keep them the same rate, 1 meter per second. So after a half a second, he goes half a meter, and then he goes to, here, this is our -1, -2. Eesh. That's a little far. -3. So that wasn't a very good half. So he goes half, and then after 1 second, 1, and 1 1/2, he moves another half, and then to 2. And we see a constant slope again. But now he's getting more and more negative. Well, this also represents a constant velocity. But what difference do we see between a constant velocity to the right and a constant velocity to the left? Well, the slopes are in the opposite directions. So, constant velocity moving to the right has a positive slope. Constant velocity moving to the left has a negative slope. So we can look at this graph and we can say, oh, it's a positive slope, the object's moving to the right. Oh, it's a negative slope, the object's moving to the left. Oh, it's no slope, the object's standing still. So we can look at a graph and see what the object is doing over a certain period of time. Now, what if the object was moving faster than I described in our pink example? How might that look different? Well, if he's moving faster, then he's covering more distance in that same amount of time. How is that represented in a picture? Well, instead of only covering half a meter maybe in a half a second, I cover 1 meter in a half a second. So then in the next half second, I'm up to 2 meters. Gotta line these up better. I still have a constant velocity, but it results in a steeper slope. So I can gauge how fast an object is moving through a scenario by how steep that slope is. If I was moving slower, I'd cover less distance for any amount of time, and I'd have a shallower slope. So we can get a lot of information about relative speeds of an object. So no slope, 0 slope, the object's standing still. Constant velocity is a straight line, that's not horizontal. If it's positive slope, it's moving to the right. If it's a negative slope, it's moving to the left. And the steepness of the slope gives us an indication of sort of relative speeds. Right, well, what if an object is speeding up or slowing down? Well, that's going to look like a curve on a position graph. So I'm going to erase my green here to give us a little more, not get so messy. I'll leave those up there. If I am moving leftward, I'm going to have negative slopes. If I'm moving leftward and also in the left world, I'm going to be below the axis with negative slopes. So, if I think about speeding up as taking velocities and changing them, changing the slope in very, very tiny amounts of time. And when we get to the relationship between these variables in a calculus sense, we'll come back to this. But if I think about taking these slopes and changing them, if I'm getting faster and faster and faster, my slope should be steeper and steeper and steeper. So if I had position changes that got steeper and steeper and steeper, these are my mini little position changes, I would see that speeding up would be represented by a curve where the slope is still negative. It's pointing in the negative direction, so it's to the left, moving leftward, and getting steeper and steeper and steeper, faster and faster and faster. So this would represent moving to the left and speeding up on a position versus time graph. As I get more and more time, I'm covering larger and larger distances. As my time moves along, I get further down the axis, in this case, left of the origin. I know I'm moving to the left because my slope is negative as I move on. So we can get a lot of information out of position versus time graphs. We can get an information about where an object started. Because where's its position at time equals 0? We can get information about where an object ended in terms of what the last time I care about is. We can get information about how the object is moving. Is it standing still? Position not changing. Is it moving at a constant rate? The position is changing along a straight line. Is it moving to the right or to the left based on if that slope is positive or negative? Is it speeding up or slowing down based on whether that positional change is getting bigger and bigger as time goes on? So we can look at all of that stuff and develop a story about how an object is moving. Or we can take a story and graph how an object is moving. So in some example lectures, mini lectures, there is an example of taking a motion story and graphing it, and then taking a graph and describing that motion story. But there are some things that will lead to that. We can get position information, we can get how the object is moving, and we can get position information, where the object is in the world, and whether it's moving right or left, whether it's constant, speeding up, or slowing down. Okay, let's try some of those. Check out those other mini lecture examples, and then practice with the homework problems. Good job.